but no acceleration. 21st lecture on filter circuits and resonance. I had introduced the concept of filter circuits in the previous lecture, and we saw that this circuit with an inductance in series and a resistance in shunt, if you excite with an AC VI whose frequency is variable, and you take the output across the resistance, then you can work out that V0 by Vi, the phasors, is simply equal to R divided by R plus j omega L. This is the division, potential division. And then if you take the magnitude, well, it can be put in the form 1 by 1 plus j omega by omega 0, and where omega 0 is equal to, what is the value of omega 0? R by L or L by R? It is R by L, right? And the magnitude plot, if you plot the magnitude V0 by Vi, then the magnitude plot starts at 1 at omega equal to 0, and it goes to 0 at infinity with half power point at omega equal to omega 0, where the magnitude drops down to 1 by root 2, and therefore the power in the resistor, which is I squared R or V squared divided by R, the power gets reduced by a factor of half. So omega 0 is also called the half power point. It is also named as the cut-off frequency. Cut-off frequency. I also mentioned that this is a filter because it discriminates against some frequencies and allows others to pass, and it is a low pass filter because it favors low frequencies. So it is called an LPF, low pass filter. Another possible candidate for low pass filtering is one in which there is a resistance in series and a capacitance in shunt. This is also a low pass filter of the same type of frequency response, except that omega 0 in this case is given by 1 over RC. Now, by a similar reasoning, one can say that if the capacitance and resistance are interchanged, that is, we have C and then an R, then this circuit shall act as a high pass filter with a half power or cut-off frequency given by the same quantity omega 0 equal to 1 by RC. Its response shall be of this form, where at omega 0 the response is 1 by root 2 times its maximum value. The maximum response occurs at omega equal to infinity. All right. So it favors high frequencies, and therefore this is a high pass filter. In a similar manner, one can argue that if I have a resistance in series and an inductance in shunt, this also acts as a high pass filter with the cutoff frequency which is given by R by L. Now this is one should not look at this only as mathematical conveniences or mathematical elegances. There is a physical meaning. There is a physical meaning. Given a circuit, you can always argue what kind of filtering will this circuit perform. Please remember that filtering can be done only when there is at least one energy storage element, because it is only energy storage elements which are sensitive to frequency. Resistance is not sensitive to frequency. So you require at least one inductance in this circuit. There can be more. You require at least one inductance or at least one capacitance. All right. For example, if you used to look at this circuit, for example, you can see that at DC the inductance acts as a short. Therefore, whatever voltage you apply here, nothing shall appear at the output. and therefore it discriminates against DC. As the frequency rises, the impedance of the inductor also increases. The output voltage is a potential division of the input voltage between R and L, and therefore as the impedance of L increases, the voltage at the output also increases, and therefore it should act as a high pass filter. In a similar manner, any given circuit can be, you can physically reason out whether it shall be a low pass or a high pass or any other kind of filtering. For example, let's consider as an example of some other kind of filtering a circuit like this. Let us say, for simplicity, let us say the resistances are equal and so are the capacitances. This is my input and this is my output V0. Okay, this is a phasor, this is a phasor, and the frequency of this source is variable. We wish to find out what kind of filtering will this achieve. The argument is very simple. It goes like this, physical argument, then we can do it mathematically. The physical argument is that at low frequencies, at DC for example, at DC this is open, the capacitor is open. So at DC this impedance R and C in parallel behaves simply as an R, whereas this series combination at DC behaves as open, and therefore at DC nothing shall appear across the output. Therefore the DC response, if you plot V0 by Vi, this ratio versus frequency, then at DC it starts from 0. Alright. Now let's look at the other extreme, infinite frequency. At infinite frequency this capacitor acts as a short, and therefore the series arm consists of a pure resistance R. But this capacitance also acts as short, and therefore the shunt arm acts as a short. Nothing shall appear here, and therefore the ratio shall again be 0, and therefore it must come like this. Now in between obviously there must be a maximum. The curve rises from here, the curve goes down at infinity, and therefore in between there must be somewhere a maximum, and therefore it acts as a band pass filter. That is, if this frequency is omega 0, then and this response is, let's say, R, then you find out where the response is R by root 2. This is not necessarily 1. At some frequency there will be a maximum. Let's call this maximum value as small r. Find out at what frequencies there shall now be two frequencies at which the response shall be 70.7% of the maximum response. That is, you find out these two frequencies, omega 1 and omega 2. This band of frequencies centered around omega 0, between omega 1 and omega 2, we say the filter passes these frequencies. Therefore it passes a band of frequencies, and therefore it is called a band pass filter, BPF, band pass filter. And this, the qualitative nature of this filter we derived simply by physical reasoning, and it is possible to do so in most of the cases. Alright. Now obviously it discriminates against low frequencies, it also discriminates against high frequencies, and it only passes a small band of frequencies. In a similar manner, if we had interchanged the series and the shunt arms, if we had interchanged, then you could argue out that it would have been a band stop filter, not band pass. If we had interchanged the series and the shunt arms, that is, if our series arm was like this and shunt arm was like this, and this is input and this is output, alright, then you see at DC this is a resistance, at DC this will be open, and therefore this is open, and therefore whatever you connect here, voltage, shall appear across the output, and therefore the DC response is 1, the infinite frequency. At infinite frequencies this acts as a short, and therefore anything you connect here shall appear at the output. So at infinite frequencies also the response shall be 1, and in between therefore there must be a minimum. There must be a minimum, something like this. This minimum may be 0, may not be 0, but you find out the frequencies at which the response is 1 by root 2, and you find out these frequencies omega 1 and omega 2 denote the minimum frequency by omega 0. It is as if the filter rejects or discriminates against this band of frequencies centered around omega 0, and therefore this band is said to be stopped, or it is not it is non-pass. It does not pass, which means it stops, and therefore this is called a band stop filter, BSF. Obviously it passes low frequencies, it passes high frequencies, it only rejects a band of frequencies centered around omega 0, and therefore it is called a band stop filter. All right. Now this is fine. What let's see one of the practical applications of a filter. One of the practical applications. You recall that our rectifier circuit, a full wave rectifier circuit, if you recall, it had a center tapped transformer and 2 diodes. 2 diodes like this. The diodes are connected together, and then you can connect the load here from this point to ground. Let's say from this point to ground, the voltage that you get is full wave rectified voltage. In other words, its waveform shall be like this. Each half of the sine wave that you feed here, each half of the sine wave that you feed here gets stepped up or stepped down by the transformer. It is center tapped. There are 2 diodes, one to take care of the positive half cycle, the other to take care of the negative half cycle, and this is the full wave rectified waveform. Now obviously there is an average value, there is a DC value which is twice, if this is Vm, if the maximum value here is Vm, then what is the average value of this? Twice Vm divided by pi. We had done this earlier. Now we want only this DC, we do not want this fluctuating waveform, and therefore we must get rid of this fluctuating waveform, which is an AC. The whole waveform can be thought of as a DC of twice Vm by pi, or upon which is superimposed an AC. All right. So we want to get rid of the AC, therefore we can use a filtering. Obviously the filter that we should use is a low pass filter, and a simple filter could be like this. A low pass filter has an inductance in series and a resistance in shunt. All right. The voltage across this resistance, if the inductance and resistance are properly chosen, then this filter should attenuate or should reduce the AC component. In other words, if this is the input, then the output waveform should be a DC upon which is superimposed maybe a small AC. Maybe what you get is something like this. The AC component is greatly reduced, and the order of reduction is is denoted by a term called ripple factor. Ripple factor, no, not quite. It is the ripple factor reduction capability of a filter, that is the ripple factor at this point shall be much less than the ripple factor at this point because of filtering by the inductance resistance circuit. Now we would like to make a little more in-depth study of this filtering effect, but let me mention to you first that if you want to use this kind of a filter, the inductance that is usually needed, if you want a simple filter like an LC filter, LR filter, did I tell you that this is an L type filter because it resembles the letter L? Alright, I did, okay. If you want to use a simple L type filter like this, there is a problem. The problem is that the inductance that is required is usually a very large value, because power frequency is small, 50 Hertz only, omega is 100 pi, alright, and therefore inductance that is required is usually large and becomes expensive. So one prefers, instead of an LR, one prefers to use an LC filter. That is, what you do is you use two reactive elements, one a capacitor and the other a capacitance. Then the cost of the filter comes down. Although you are increasing one element, the value of L that is needed is usually much smaller, and inductance accounts for most of the cost for the filter. We shall look at this circuit a little more cautiously. Alright, let's consider the LC filter, LC and R. This R is the load. This resistance R is the load. It could be a transistor circuit, for example, for which you have the power supply. So what we have is the rectifier, transformer rectifier combination. We call this a rectifier. And then at this point, the waveform that I have, this is L, this is C, that is R, okay. And what I want is, this is my V0. This is the output voltage. What I want is that V0 should be purely DC. Unfortunately, the filter cannot reduce it to 0, cannot reduce the ripple or the AC component to 0, but it reduces substantially. And the measure of performance is ripple factor at the output and ripple factor at the input. The ripple factor at the output should be much less than the ripple factor at the output. By definition, ripple factor is what? The root mean squared value of the AC component divided by the DC, the average value. Ripple factor is the ratio of RMS value or RMS AC component divided by the DC or the average value. Alright. So the ripple factor is a measure of the effectiveness of the filter. You measure the ripple factor at the output and ripple factor at the input. These two should differ greatly. The output ripple factor should be much less compared to the input ripple factor, then the filter has been effective. Now to analyze this circuit, we require an analytical expression for this input waveform, which is of this form, okay, and it can be shown by Fourier analysis. Are you acquainted with Fourier analysis? Not yet. Anyway, any periodic waveform, whether sinusoidal or non-sinusoidal, can always be decomposed into sinusoidal components. And you will learn this later, that such a waveform can be decomposed into the following. If I call this as Vt versus T, then Vt can be written as, let me use some other page. This full rectified waveform can be written as twice Vm by pi. This is the DC value which we have already derived. In addition, there are alternating components. Now if you look at this waveform, the input waveform was something like this. And the output waveform is like this. So the input waveform, the period was this much, whereas the period of the output is this much. Obviously, the output waveform's frequency is double that of the frequency of the input, and therefore if the input waveform has a frequency omega, the output waveform has a frequency twice omega. And what we have is, by Fourier analysis, one can show that this is 1 minus 2/3 cosine omega t, 2 omega t, this is the frequency, this is the second harmonic, because the frequency of this is harmonically related to the input frequency to the transformer. Input frequency is omega and this is 2 omega. Any frequency which is an integer positive multiple of another frequency is called a harmonic. 5 omega is the fifth harmonic, 10 omega is the 10th harmonic, 2 omega is the second harmonic, and what is the frequency of the first harmonic? First harmonic and fundamental are the same, that is omega. Alright. Then in this waveform, in the full wave rectified waveform, it is only even frequencies which are there, because the fundamental of the rectified waveform is 2 omega, and therefore you have 4 omega, 6 omega, 8 omega and so on. You can't have a 3 omega component. Alright. So you have 2 by 15 cosine 4 omega t and so on. The number of frequencies in theory is infinitely large. However, the amplitude of these components, the second harmonic is 2/3, the fourth harmonic is 2 by 15, and it diminishes as the order of the harmonic increases. Alright. And therefore in practice, if we can take care of the second harmonic, if we can reduce this substantially, obviously all other harmonics shall become negligible. If we can make the second harmonic negligible, the fourth harmonic shall also be shall be further negligible. Alright. So it suffices in practice to approximate this by only two terms. The first two terms, let us say the DC component 2 Vm by pi and the AC component in this, which is the second harmonic, that would be 4 Vm divided by 3 pi cosine of 2 omega t. Is that correct? Have I done it correctly? 4 Vm divided by 3 pi. Okay. So let us see how we can reduce this second harmonic by means of an LC filter. LC filter of the architecture L, inverted L. Okay. So what we wish to investigate is the following. We have an inductor, a capacitor and a resistor R, and our input consists of a DC whose value is twice Vm divided by pi, and an AC which is minus 4 Vm divided by 3 pi cosine 2 omega t. This is my input. I have shown this as two sources. One is a battery, the DC of value 2 Vm by pi, in series added to an AC component whose value is minus 4 Vm by 3 pi cosine 2 omega t. We wish to find out the output voltage. Okay. If I call this as V0 of t, let us say, the output voltage V0. Obviously for DC, because this is a linear circuit, we can find out the output by superposition. Alright. Now by superposition means we consider one source at a time. So if we kill this source, then for DC the inductor is short and the capacitor is open, and therefore the DC component at the output shall be V0 DC shall be the same, 2 Vm by pi. It is the AC component that we are concerned with. Now for AC analysis we make several assumptions which are true in practice, several simplifying assumptions. One is that capital R, the load, is much larger. Assume that capital R is much larger than 1 by omega c. What does it mean? It means that the effective impedance of this shunt is determined by C only, and therefore this impedance is 1 by j omega c. Alright. Also assume, this is true in practice, you have to choose your C. such that its impedance is at least 10 times less than capital R. Capital R, if it is, let us say, 400 ohms, 400 ohms, how do you determine this? Suppose we want 20 volt output and the output should be 50 milliampere, then you know what your load is, alright. You want 20 volt across a load in which 50 milliampere passes, obviously the resistance must be 400 ohms. Then your capacitor must be so chosen that its impedance 1 by omega c is at the most 40 ohms, not more than that, 40 ohms at 50 hertz, alright. Then also assume that omega L, that is the impedance of the inductor at the given frequency, at the power frequency, is much greater than 1 by omega c, alright. This is also to be satisfied in practice. For good filtering, this is to be satisfied, that is, the impedance of the inductor should dominate over the impedance of the capacitor, alright. Under these conditions, you see the phasor, the voltage phasor for the output, the AC phasor for the output, that shall be simply equal to, if I draw this circuit again, L, then C parallel R. Suppose this phasor, second harmonic phasor, is V2H, V2H second harmonic phasor, and suppose this phasor is, let us say, VAC at the output. Then obviously the ratio of the two, VAC over V2H phasor, that shall be equal to the impedance of this, which is approximately 1 by j omega c. Why? Because capital R was much larger, divided by the total impedance. Total impedance is j omega L plus 1 over j omega c, but we have assumed that omega L is much larger than the impedance of the capacitor, so this must be the story, where obviously we had made a mistake. Can you tell me what the mistake is? Pardon me? What is the mistake? No, that's not it. We made the mistake right here. No, R is much greater than 1 by omega c. That is not the mistake. Mistake is the frequency is not omega. Frequency is 2 omega, and therefore everywhere we must substitute 2. The frequency of the AC input is 2 omega, and therefore this is 2 omega, which means that our relation should be J2 omega c divided by J2 omega L. And obviously you see this is 1 by minus 4 omega squared LC. This is what it is, and therefore VAC phasor would be equal to minus 1 by 4 omega squared LC times V2H phasor, which is given by 4 Vm divided by 3 pi. This is the maximum value. This has to be divided by root 2, 1 by root 2, and you can show very easily that this is 1 over 6 no, I'm sorry, VAC is equal to Vm divided by 3 root 2 pi omega squared LC. It's a phasor. Alright, we have not, no, I think we must use a negative sign, minus this, alright. Pardon me? Vm is not a phasor. Vm is the maximum value. Is that okay? This is VSC. Therefore, the ripple factor R at the output, ripple factor at the output, which is VAC magnitude divided by VDC would be equal to Vm divided by 3 root 2 pi omega squared LC, and this would be twice Vm and here pi. VDC is twice Vm over pi, and now you cancel out things, Vm, pi and pi, and therefore this becomes 1 over 6 root 2 omega squared LC. This is the ripple factor at the output. What is the ripple factor at the input? What is the ripple factor at the input? If you recall, four divided by 3 pi Vm root 2, this is the VAC, right? 4 Vm by 3 pi root 2 divided by twice Vm divided by pi. What is this equal to? Vm, 2 and 2, 2, pi cancels, so 2 by 3 root 2, alright, 2 by 3 root 2. Now compared to this, let us find out the improvement factor, alright, R out divided by R in, the ratio of the two ripple factors, pardon me, yes, say it loud, yes, last step, the input ripple factor. Input ripple factor is V2H phasor, which is 4 Vm by 3 pi root 2 divided by the DC value 2 Vm by pi, which is 2 by 3 root 2. What I want to do now is to compare the output ripple factor to the input ripple factor to find out 1 by 4 omega squared LC. That's quite correct. As an example, suppose our L was 20 Henry and C 40 microfarad. Typical values. Capital R, as I said, 20 volts at 50 milliampere, which means 400 ohms. Then one can show that the ripple factor at the output is approximately equal to 0.0015, which means 0.15% of or is it R out? It is R out, not R out by R in. Both are dimensionless. The input ripple factor is simply 2 by 3 root 2, which is how much? That is root 2 by 3 equals to how much? 0.47, and which means 47%. Is that right? The input ripple factor is 0.47, the output is 0.0015, and you can see the order of reduction that has been obtained. Alright, and therefore whenever you use a rectifier, you always use a filter to reduce the ripple to a quantity which is negligible, to reduce the AC component, and thereby you get pure DC. So this is one example of filter. There are many other kinds of filter. I have told you that one could, instead of a L filter, one could use a T, for example 2 inductors and 1 capacitor. This does look like a T. Or one could use a pi. This looks like a pi. The left hand side is the rectifier, the right hand side is the load, and all of them act as low pass filters to reduce the harmonic components present in the output. There are many other kinds of filters, and one of the examples that one comes across in instrumentation and measurement very often is the so-called bridged T filter. bridged T. This means a T, this refers to the architecture of the circuit, that is how does it look like. Well, it is a T, there are two capacitors C1 and C2, then there is a resistance here, let us say R1. This looks like a T, and then you have a bridge across the T. It's a flyover, a resistance R2. Alright, it's a flyover. So, your input is here, V sub I, and your output is here, V0. Now, if you wish to analyze this circuit, you have to assume phasors here, Vi, V0, and then work in terms of the impedances. You know KVL, KCL, both are valid for AC circuits, and therefore you replace C1 by 1 by j omega C1, C2 by 1 by j omega C2, R1 and R2, or you could work in terms of S instead of j omega. Finally, you replace S by j omega. It will give the same result, alright. It is more convenient to work in terms of S because you don't have to handle the quantity J. Wherever there is a multiplication of J by J, a negative sign comes up. If you miss that negative sign, then you are done with, okay. So it's better to work in terms of S. Now, how do you analyze this circuit? What is the best method? I can do it by loop. How many loop equations shall I have to write in this particular case? 3 or 2? If this is left open, then only 2. If there is a load here to ground, then 3. Agreed. But now there are only 2 loops. One is this and the other is this. This is not a loop. Isn't that right? If I know both these currents, then of course I shall know the voltage. This voltage would be drop across C2 plus drop across R1. This current is I2 and this current is I1. Yeah, this current is I1. Yeah, okay. Node analysis, all right. For node analysis, how many nodes, how many equations? 2 nodes, one is V0 and the other is this intermediate node. So there is nothing much to choose between. It's almost the same kind of thing. But let me quickly show you another kind of analysis which sometimes is more advantageous, where the chance of making a mistake is less. Alright, let's look at this quickly. This is somewhat innovative and interesting. You have C1, C2, a resistance R1. You see, if you look at this circuit Vi, this input, the potential at this point is Vi, whether you consider this branch or this branch, it doesn't matter, isn't it? So if I separate this out, if I separate the 2 wires and connect 2 sources, Vi each, shall it make a difference? It should not. Let's see what it gives in terms of, this is Vi, and the other branches, you have a resistance R, and this voltage is also Vi. I have separated the 2 input branches, alright. Now, and this is V0. Now, I can find out the voltage at this node independently of what happens to the other. Can I? I can find out the voltage at this node by simply one node equation. I can find this in terms of Vi and V0. Alright? And if I know this node voltage, how does that help me? No, it doesn't. That's not the way one should think. Let me not mislead you further. You would end up in absurdity because you are not solving anything. You are finding an unknown in terms of another unknown. V0 is the one that we want to find out. No. The simplification comes by applying Thevenin's theorem. If KCL and KVL are valid, Thevenin's theorem should also be valid for AC circuits. Alright. So you apply Thevenin's theorem. What do you get? You get a C2 V0 R, this is Vi, and then you get an impedance. What is the value of this impedance? R1 and C1 in parallel, and therefore R1 by S C1 R1 plus 1. I am working in terms of S. You must be able to write this expression without any calculation. R and C in parallel gives R over S C R plus 1, and the voltage source here would now be not Vi but Vi, yes, S C1 R1 divided by S C1 R1 plus 1. That is the potential division between C1 and R1. So Vi R1 divided by R1 plus 1 over S C1 R1, which simplifies to this. Alright. Now the circuit is extremely simple. All you have to do is to apply one KCL, that is this current, which is Vi minus V0 divided by R2. Was this R2? Yeah. Vi minus V0 over R2 should be equal to V0. It must be equal to this current. KCL at this node, the current that comes must leave, and therefore that this current is V0 minus this voltage divided by this total impedance. Alright, just one equation. The other you didn't have to write an equation, it's by inspection, and therefore just one equation, and you solve for V0 or V0 over Vi, which is the transfer function. Is the point clear? I'll skip the algebra. Alright, is the point clear? The analysis method. One has to decide what will be the best. I am sure you have not come across this type of analysis. With a voltage source, the branches can be torn off and connect two voltage sources, identical voltage sources. This does not apply, let me caution you, because you might fall in a trap. This does not apply if you have an internal resistance here. If there is an internal resistance here, then this method of analysis fails. Not only that, if instead of a voltage source it is a current source, it doesn't apply. Only in terms of voltage source, ideal voltage source, you can separate the two branches and connect two identical voltage sources. Alright, wherever a situation like this occurs, this allows immense simplification. Yeah.
So if you have an internal resistance, so even then, so the potential between these two branches, the same potential difference is same across these two.
Correct, but we don't know. We don't know what this potential is. We don't know, because it depends on what current goes in this branch, what current goes in this branch. A problem to think about. All right, how to tackle a situation where there is an internal resistance. All right. Now I leave this to you as an exercise. The answer to V0 by Vi, that is this ratio, this is given in the textbook, and it can be shown that this indeed acts as a band stop filter like this. It acts as a band stop filter with a frequency, with a center frequency of the stop band, which is given by 1 by square root of R1, R2, C1, C2. Alright, and the width of this will depend on the relative values, that is omega 1 and omega 2. It depends on the relative values of the various components, but I will skip that algebra. Now this is one way of getting a band stop. If you recall, the circuit is, the architecture is that of a bridge to T. There is a T and then there is a flyover, but it contains only resistances and capacitances. Much better performance is obtained if you mix the two kinds of energy storage elements, that is, if you use an inductor and a capacitor. one or more capacitors. For example, one of the circuits that you shall encounter in practice if you try to measure something, one of the circuits is this: 2 capacitors, 1 resistor, the same configuration, but instead of a resistance, if you use an inductance here, it can be shown that this gives a much sharper band stop, perhaps something like this as compared to an RC bridged T, if you introduce both kinds of energy storage elements. And one of the simplest examples of 2 kinds of energy storage elements in a circuit is the so-called resonant circuit, the simplest of which is this circuit, the series circuit. Suppose you have 3 elements in series: resistance, inductance and capacitance. We have already analyzed this circuit. It's a second order circuit. It can be underdamped, it can be critically damped, it can be overdamped. All right. Now let's look at this circuit, the steady state response of this circuit to, let's say, a sinusoidal source. Suppose you have a source Vi whose frequency is variable. All right. We wish to find out how does this circuit respond to various frequencies, and suppose what we wish to find out is the current response. All right. Then you know the current response is the current phasor is the voltage phasor divided by the impedance, and the impedance for sinusoidal frequencies is R plus j omega L plus 1 over j omega C, which I can write as, if I skip one of the algebraic steps, j times omega L minus omega C. And you see that the magnitude of the current phasor I shall be given by the magnitude of the voltage phasor V I divided by the magnitude of the impedance, which is R squared plus omega L minus 1 by omega C whole squared. All right. As frequency is varied, let's look at this expression a little more carefully. As frequency is varied, at when omega L is greater than 1 by omega C, all right, when omega L is greater than 1 by omega C, obviously the angle of the current shall be negative. Isn't that right? Angle of the current shall be negative, that is, the current shall lag the voltage. On the other hand, when 1 by omega C is greater than omega L, the angle of the current shall be positive, that is, the current shall lead the voltage. When these two are equal, then the current shall be in phase. Not only that, if you look at the magnitude, you see that the current will be a maximum when omega L is equal to 1 by omega C, and therefore if you vary the frequency of the circuit and you measure the current phasor, all right, the current obviously for omega equal to 0, what will be the current in this circuit? 0. Why? Because there is a capacitor, and at infinite frequency the inductance acts as open, so again the current shall be 0, and in between you have a maximum, and you can see that this is indeed the circuit of a band pass filter. The current shows a band pass response, and the frequency at which the current is a maximum is given by omega 0 L should be equal to 1 by omega 0 C, that is, the impedance of the inductor and the impedance of the capacitor, they should cancel each other, and therefore omega 0 should be equal to 1 by square root LC, and the maximum current then shall be given by Vi divided by R. This is the maximum current. All right. Now this is obviously a reflection of the fact that the impedance of the RLC circuit impedance of the RLC circuit, if you plot that, the magnitude of the impedance, obviously it goes through a maximum or minimum? Minimum. It is infinitely large at DC, infinitely large at infinite frequency, and in between it goes through a minimum where the value is capital R. And this happens at the frequency 1 by square root LC. At this frequency 1 by square root LC, the impedance is purely resistive, which means that its angle is equal to 0, and this phenomenon is called the phenomenon of resonance. Resonance is a phenomenon in which at a certain frequency the angle of the impedance becomes 0. That is, the current and voltage are in phase, and you see the resonance effect is accompanied by either a band pass filtering effect or a band stop. Well, if you take the voltage as a response, current is held constant, then obviously it will be a band stop type of thing. Whereas if you take the voltage as the excitation and the current as the response, then it is a band stop type. Not only that, on Friday we shall see that it is possible to multiply the input voltage by any number. For example, from 1 volt without using a transformer, you could get, if you so desire, 100 volts. 1 volt AC could be transformed into 100 volt without using a transformer by using the phenomenon of resonance. That is, resonance can be used to multiply voltages. All right, this is what we shall see on Friday.